Hello, everybody. I want to welcome you to this panel sponsored by NETS Virtual Organization, so Networking and Telecommunication Systems. And this is a virtual organization sponsored by NSF. And this is old where it says new website coming this fall. We have a great website, which is nets-vo.org. And I understand that some of you saw that website when you registered. So before we get started, a little bit of housekeeping. So housekeeping, please mute yourself during the panel presentation and ask your questions in the chat. We have enough people that registered that we want to make sure that we can get to your questions. We may not get to your particular question, but we will try and incorporate similar questions into one. So if 3 people ask a similar question, we'll try to get that in there. And we may call on you to ask the question directly, in which case, please unmute yourself. And this meeting is being recorded, just so you're aware. Okay. Next overhead. All right. So introduction. So I'm your host, and I'm a professor here at Santa Clara University, and Matthew Isaac Tolosa of Santa Clara University and Tanya Pham, I forgot to introduce Tanya also, from Santa Clara University, who are 2 students here, are moderating also. So they're helping with the chat, the whole thing. So this presentation is part of the Sally Floyd channels. And so it's webinars in honor of the pioneering telecommunications researcher, Sally Floyd. If you haven't heard of her, she's on Wikipedia. Please check her out. And so now on to our panel. So we have a great panel today. First up is Ana Garcia Armada, who's a professor at, and Ana, I'm not going to be able to pronounce this well, Universidad Carlos III of Madrid. Our second panelist, Shalini Kishore, could not make it today due to a family emergency. So we're sending our best to Shalini, but she sent me some notes. So occasionally I may interject with some thoughts that I'm cribbing from Shalini. And then we have Angel Lozano, who's at, again, I'm going to get this wrong, Universitat Pompeu Fabra. He's in Barcelona. And then finally, we have Ted Rappaport from NYU Wireless. So with that, I'm going to turn it over to the panel and ask each of the 3 remaining panelists, Ana, Angel, and Ted, to tell us a little bit about themselves and what they want to talk about before I start poking them with questions. So Ana, can you go first?
Sure. Thank you, Katie, for the invitation. It is very, very interesting, this panel, and very nice colleagues, co-panelists. So I work at a university in Madrid, and I do signal processing for wireless communication. So I started a long time ago with OFDM, then multi-user OFDM, then MIMO OFDM, massive MIMO, and now, of course, millimeter wave. And, I'm usually taking care of what can you do in the transmitter and the receiver, what kind of algorithms you can do to make things work better. And maybe to start the conversation, I understand now everybody will introduce and we can maybe change the question, but the first question I have is, do you think we are getting too much into the mathematical aspect of our communications and forgetting a little bit about fundamentals? So this is my first question.
That's a great question. And I'm looking forward to discussing that in just a minute. But if Angel and Ted want to take that up when they talk, I'm going to turn it over to Angel. And so Angel, you can pick up the ball there.
Hi there, Katie and everyone. It's a pleasure to be in such great company. It's evening time for myself and for Ana, 8:30 p.m. And it's been a long day already, and I haven't had dinner yet. But I'm sure that the great company and the topics of discussion will energize me. So Ana and I are old friends. And Ted, well, my last sabbatical before the pandemic was at NYU. So I sat across from Ted for a few months in this world-class center that he has put together in Brooklyn, almost from scratch. So we're in a great place. And as of myself, well, very briefly, I got my PhD at Stanford a few years after Katie. And after that, I spent a decade in New Jersey doing research at Bell Labs. And then subsequently, I moved back to Barcelona, where I'm now a professor. I worked on wireless. And I'm going to start thinking about Anna's really tough question while Ted introduces himself. Over to you, Ted.
Oh, you're muted, Ted.
Thank you, Angel and Katie. It's so good to see you. I wish we were all in person. Anna, it's so great to see you also. Hi, everyone. I'm Ted Rappaport. Really honored to be invited and delighted to be here with you, Katie, Angel, and Anna, and everyone on the Zoom. I've been a professor now for, wow, 33 years, almost 34 years. So I'm like a gray hair. You can see some gray there. I don't color it, but it is starting to turn gray. I don't feel that old, but I've really enjoyed riding the wireless wave ever since my master's and PhD before Wi-Fi. And I was very fortunate, very blessed, because I had a chance to do research which the founders of Wi-Fi actually used. And as a young professor, I got to sit in and help develop the Wi-Fi standard and then the world's first digital standard. That I've been just kind of, as a researcher, been able to keep looking at the physical layer aspects all the way through the last 5 generations of wireless. And now I'm looking at what 6G will be. I've also done robotics from my early days as a professor. But what I've enjoyed most in being in academia is working with great colleagues. For example, NYU, I came here, I don't get nearly all the credit on how it was faculty like Elza Urquhart and Shiv Panwar and Sandeep Rangan, who were here before me, Yao Wang and Yong Liu, who we together built this wireless center. And yeah, we did put NYU on the map in wireless, but I was lucky to have done that earlier in my career at University of Texas, working with great colleagues who came in at the same time I did, like Jeff Andrews and Robert Heath and Sanjay Shakatai. And I did it before at Virginia Tech, where I hired Jeff Reed and Brian Warner and built the center in the very early days of cellular. So I've been lucky to be in academia, and I've started a few companies along the way and advised some. So I've kind of seen industry and stayed very close to industry all my life, because I believe that's where most PhDs go. We'd love to all be teachers. It's a great work if you can get it, but really getting leaders in industry has been one of the key things about my career. So you can't do that unless you really know industry, and I've tried to do that.
And that kind of leads into Anna's question about math and engineering. Personally, I think math is a little bit like wine. It's an important thing, but after too much, you got to stop, right? You have to step back and appreciate it. So Anna, Ted, and Angel, what do you think about that?
I don't think we can never have enough math, but
Or wine,
or wine. But I agree that we need more than math. And for instance, I see physics making a big comeback these days. More and more, I find physics and electromagnetics being an important part of my research, more so than in the past. And I'm trying to convey to my students that those skills might be important for their work going forward. Now, as we move up in frequency, it becomes more and more relevant to everything that happens then in the baseband, essentially. So yes, physics.
I agree with the concept of electromagnetics and physics becoming more important. I work on radio wave propagation, amongst other things, and there, the physics of radio wave propagation need to be brought into what we do. It's mathematical, and unfortunately, the industry oftentimes just does curve fitting with no understanding of the basics of the physics and electromagnetics. A lot of the channel models oftentimes have no physical basis. So we've done a lot of work to try to teach the industry a little bit of physics, like the first meter of free space loss is the key to all models up to millimeter wave and above. But you know, I think math is a wonderful language. It's like speaking a different language. And if you're good at it, you like to speak it a lot. The trouble is, if you speak too much math, you lose the essence and the intuition. And I think great engineers need to have intuition. So I think math is vital and powerful for developing intuition and developing a framework for understanding and analyzing. But the problems these days are so big that you have to rely on computer and computer-aided design simulation, because it's too untractable just to use math all the time. But you need math vitally for understanding the fundamentals that you can build upon.
Yeah, I agree. And especially for these higher frequencies that are a bit unknown to us, as Angel was saying, we need to discover the new models, because probably old models don't work. And we cannot just take the old model and do the math and expect to have something coming out of there. But also, even in lower frequencies, I think sometimes we have this tendency of applying whatever math we know how to do without thinking much about, are the assumptions realistic? Can this be really built? And we produce, not everybody, of course, but I'm generalizing, right? Papers that are nice, but maybe are not having an impact on the advances of our field. And I see many of those, but of course there are others. So yeah, I agree.
Yeah, no, it's interesting that the subset of problems that can be solved analytically is shrinking, right? Because things become, systems are more and more complicated, and yet papers that are analytical are still welcome, and papers that are not analytical are frowned upon sometimes.
Mhm.
Yeah, I want to give you one example. Go ahead, finish your point. Then I'm going to.
No, I'm just that there's a bit of a disconnect here.
Yeah, well, here's an example of where math is wonderfully powerful. Right now, I'm trying to get my students using a new theory that we developed back when I was at UT Austin over a decade ago. It's the first analytical way to analyze power consumption. In the whole world of power consumption and power efficiency of devices and electronics, which is going to become really important for 5G and 6G, I found there were no analytically tractable mathematical solutions. All of us in communications took an undergraduate course on digital communications, and we learned about noise factor. Remember noise figure, noise factor? It was a beautiful, elegant mathematical model for a cascaded system, and it uses math, not complicated math, to figure out the noise contribution of each component along a cascade. And by that, you could figure out the total signal noise ratio. We developed an exact analog to that called the consumption factor theory, which looks at the power contributed by each device and how much power is transmitted between devices. The direct analog hasn't taken off yet. The paper looks very mathematical. I have about 100 equations in it, but it's really very elegant. And I think all that math has kept people from reading it. But it's just as powerful as noise figure is for understanding noise, to understand the power of a handset or a computer or a relay link. It's so powerful, but I think the math intimidates. So I'm with you, Angel, that we need math. The mathematical crowd sometimes gets together and wants to just do math for math's sake, and then you have the people that aren't so mathematically inclined getting shunned out because they don't speak enough math. But the fact is we need just the right amount. Right? Just the right amount. Too much math it kind of creates a little club.
Yeah, this is very important what you are mentioning about the power consumption, because this is maybe to change a little bit the question. I feel we have never really taken seriously the power consumption. We put it, in the equations and somehow, right? And there is all this green, whatever. But the truth is that our communications are more and more energy hungry as we go up in the generations, and this is getting a very important problem. And I wonder if we could maybe encourage the new engineers and researchers to look more deeply into what really is power consumption and really honestly minimize it, not just in the way we are doing.
Any thoughts on that, Angel?
No, yes, it's happening already, I think. I mean, until 5 or 6 years ago, you had never seen papers worrying about the ADC power consumption. And now it's everywhere, right? And, more bandwidth, higher frequencies, clock rates. So, more and more, the radiated power is the least important part of what you consume, right?
Exactly. That's what the consumption factor theory shows. It's actually not the radiated power that's critical. It's the ratio of the non-functional power for communication versus the actual power radiated. It's that ratio that determines small cells or large cells in joules per bit. So check out the consumption
No, I
factors.
can't believe I haven't seen this paper of yours.
I know no one has. It's only been cited like 80 times. It's like so fundamental, but I just haven't, I've been too busy doing other stuff, but you will love this. It's so elegant because it will allow you to trade off how much power goes in the amplifier, how much is in the graphical interface versus how much is in the oscillator.
Right.
It just takes every component. This is the beauty. It takes any component, whether it's a transistor or a cell phone or a amplifier, and it breaks the power consumed by that one component or system, could be a cascade. It takes the power and breaks it into 3 orthogonal components of power that all equal the total power. Just like noise figure does power in versus power contributed. So the 3 separate parts of power in anything we do is A, the power transmitted along the chain, which has information. B, the power that powers that component or thing that transmits information. And C, the ancillary wasted power that has nothing to do with transmitting communication. So you can see, think of a display for radiating a radio signal. You know, the display or the power supply has nothing to do with the power radiated, but it's power off the signal path. The waste of power in an amplifier, the amplifier is vital for transmitting power. It is waste due to heat. So that's power wasted on the signal path. And then the third power is the power that actually goes out of the signal path. If you break any component or cascade of components into those 3 distinct powers, we have this unified theory for analyzing, comparing any design, any network, any cascaded system, any cell phone for power consumed, and importantly, the power per bit, the energy per bit. And we used that back in 2014 to prove that 6G and terahertz is going to be so much more power efficient than anything else, even with wasted power amplifiers that we haven't built yet. It's so much more power efficient, and the small scale structure is more power efficient than the large scale structure. So wireless is actually going to be entering a much more power efficient joules per bit era, and we have a theory that shows that.
Well, that's a daring statement, I'll say.
Read the paper.
You have to
We
put,
will.
maybe you can put the link on the chat because I'm never going to find it by myself.
Yes, please do. Please put the link on the chat.
Okay.
So that leads into the next question about 5G, really 6G. And of course, there's always going to be a 7G, though everybody likes the even ones better. We want more data, and more data has typically meant more power, right? You get the big and then MIMO. A lot of people talk about how MIMO consumes a lot of power. So how do you see 6G, the higher frequencies? I'm going to start with Anna on there. So how do you see 6G and the desire for more data going? You know, your crystal ball.
Yeah. Okay. So two questions. First, the desire of more data. I am sure we will desire more data always, you know, because we always will find we need first to build the system that brings you the data as fast as needed, and then people will come with applications and we will have amazing things. I'm completely sure about it. Now, the Gs, 5G, 6G, 7G, really, I think we are putting too much expectation on the people with all these Gs. We cannot go as fast, it's impossible. And then what they get is disappointing, right? Because they sell them this new 5G and they tell you, well, my phone works exactly the same as with 4G. And, you know, I know this is a very important brand or mark or, a commercial name that the operators use, and I understand they will keep using. But why do we need to use it, the researchers? It's, you know, we could always look for further advances in whatever without the need of calling it so fast, you know, because now we have 5, we have to go for 6. 5 is not complete and it's not working. So yeah, I mean, at least here we get the same, you know. So sure, we need to keep advancing, getting more data, efficient in power and cost, and maybe we could forget about the Gs.
I couldn't agree more. That there is this thing with the wireless generations that when we are at generation G, we tend to downplay it and we hype up the next generation, G+1, indicating that that will be the true revolution. Then once we get to generation G+1, we immediately downplay it and we start pedaling generation G+2 and so on, right? So that's happening now with 5G. There's people saying that, you know, as you alluded, Katie, all odd number generations have been a fiasco and we're going to need 6G to fix everything that's wrong with 5G. So it's a wheel that turns around and around. In fact, with 4G initially, there was an attempt to break with that. And the name long-term evolution was coined to signify that this was a standard that could be improved and revised indefinitely without the need for new generations. But in the end, the pressure to bring to market a new brand was too strong. So we had that 3GPP release 14 was 4G and then release 15 was 5G. It could have been 4G+++, but it was 5G.
In a spirit of
Katie, getting to your
nostalgia, I used to
question
refer to 4G as 3G LTE all the time. But go
Right.
ahead, I'm sorry.
Could be. No. Now getting to your question about 6G, I'll say it's impossible to answer questions about 6G when we still have so many questions open about 5G. So a big thing in 5G was to move beyond providing mobile broadband to smartphones. A key driver were all the verticals in various industries, say automotive. But we are yet to see how that pans out and whether some surprise killer app appears for 5G that we haven't even thought about. So I think it's way too soon to think about 6G when we're still not sure about what G is going to truly be. So I think that at this stage, we should be pushing hard on the fundamental research without constraining ourselves with the thought of another, of specific applications. We should just come up with ideas that are bold and ambitious and see where they take us with an open mind.
That's a great one. Ted.
Yeah, I think Anna and Angel both basically said in a nutshell, the G, the generation, is a marketing term.
Yeah.
So 4G, 5G, it's marketing so that in the US, Verizon and AT&T and T-Mobile can run their ads and say they have the best 5G. And my industrial affiliates cringe when we talk about G because they need to sell the existing product and the many, many years of existing 4G still mostly around the world. And 5G is very new. So for us to be talking about 6G, they kind of look at us crooked and kind of cringe when we talk about 6G. But 6G is marketing. It shows that we're way ahead of where we are today. And so look at what you have. You have University of Texas, my colleague, Jeff Andrews, they just started 6G UT. My buddy, Robert Heath, who just started 6G NC at North Carolina State. And, I have the Brooklyn 6G Summit. So, I mean, we academics are also prone to this marketing hype, and you kind of see it happening at some of the big wireless centers around the world. Look at Hulu. Mati got the first big 6G funding with $250 million. I wish our US NSF, Katie, tell your NSF people they need to put in money like Hulu does. They got $250 million to start drinking pine tar and studying 6G back 2-3 years ago in Finland, of course, the home of Nokia, and great university in Oulu. If anyone's on from Oulu, it's just amazing. The Finnish universities are phenomenal in wireless, and I wish our country, the US, could kind of see how they do things. It's really brilliant. But I do believe every generation always has at least an increase in order of magnitude of the data rate, the physical link air interface data rate, which opens up new advances of new generations. 5G will be the same. Anna, you're right. Engineers right around the world don't like 5G, especially at millimeter wave. They don't understand how to site it yet. It's more site specific. You have to worry about where the foliage is in the buildings, but they'll figure it out, just like they figured out every previous G. And along with it will come not just 50 or 100 megabits per second, which you enjoy with 4G LTE. That's 4G, Katie, not 3G. 4G LTE. But we're going to see gigabits per second. In fact, I've already seen markets where we're several gigabits per second with millimeter wave. So as the engineers get better at that and people understand that directional antennas are not omnidirectional, I could give you a whole lecture on that. And I've been giving keynotes all over the world on that the last few months. It's because we've got data at 140 gigahertz that, guess what, Anna? Guess what, Danielle? The channel does not change that much from 28 up to 140 gigahertz. It's a remarkably similar channel. Same path loss with distance, about the same amount of multipath, a little bit less spatial directions, but not many. You still have so much diversity. So massive MIMO, which we're really learning in 5G, 4G and 5G in the midband, massive MIMO will come to 5G. And again, we'll go orders of magnitude data rate improvements. And the diversity is there going all the way up above 100 gigahertz. So I really believe 6G will be getting us over 100 gigahertz in mobile channels. And the beautiful thing about wireless that I've been telling people, and we're writing a paper on it now, but I've given speeches around, is that once you go higher in frequency, the fact is that the densification needed for 5G, that is the cellular base stations getting closer to where the people are, densification, the Small Cell Act by the FCC and other governments around the world, bringing the cell phone closer to the base station, that's not a function of millimeter wave or sub 6 gigahertz. That's just a function of noise figure and bandwidth, KTB, the power you need to get over a wider bandwidth channel, you need to be closer to the station. So it would happen in midband spectrum if we have wider channel bandwidth. So it's not an issue of carrier frequency. It's an issue of wider bandwidth channels. You need densification at any carrier frequency. The beauty we found at NYU is that it doesn't matter what frequency you're at. The channels are remarkably the same. So the densification that's coming for 5G and the consumption factor theory both show that going to wider and wider and wider bandwidth channels, we're going to get free data rate and won't have to further densify the network. Once small cells are done for 5G, we get greater data rates at 6G and 7G for free. Wider channels for free at the same distances. It's amazing.
Isn't it astonishing that for many years, we thought that we couldn't operate above 6, 7, 8 gigahertz? And we taught that to our students. And I'm just wondering now, what kind of data was that based on? I mean, there must have been some data, right?
It's based on human nature. It's the data of humanity. The data of humanity is that we can't like what we don't know. Unfortunately, that's human nature. That's the only data point. If you don't know it, look, we thought the world was flat until people sailed around the world. Same thing in wireless.
But I think we cannot forget that, as you said, directional antennas are not omnidirectional and you need to point them. And maybe some years ago, we were not ready to point the antenna to people that are moving. I'm not sure we are yet ready to point it to vehicles that are moving fast. So maybe at that time, Angel, we really couldn't do this because we needed the beams and we couldn't, I mean, we could do that for fixed, but not for mobile. And yet, I believe it is still a problem.
I'm looking at a question in the chat. I want to answer this. It's a great question. Someone asked, is 5G reinventing what 4G LTE intended to but couldn't do? And is 6J a five-layer revolution, or is it more a system-wide architecture? I think we should take that question because I want to say first and foremost, 5G is very different than 4G. It's not just improving on 4G. No. The amazing thing about 5G is the first time, and Angel, you can talk about this. It's the first time the industry got together and said, you know, the first 4 generations of cellular was basically about texting, internet, and higher data rate, wider pipes. 5G is the first global cellular standard that takes cellular out of the idea of just human communication and internet and texting and opens it up to machine to human interaction. For example, there's ultra reliable low latency, which is super reliable data, which can be done in factories and for autonomous vehicles. There's also, in addition to low latency, there's an IoT mode baked in. There will be actually a low power heartbeat kind of low data rate communication built into the 5G standard that never existed before. There's the concept of network slicing, which allows a cellular operator or an enterprise like a big factory or a university to actually get spectrum from the carrier and operate on the network and kind of have a dedicated virtual network in the air interface and the standard. So there's so many new things brought into 5G that never existed. And it's going to make the cell phone and cellular products and heartbeat products totally new that we never had. In fact, look at a talk that Ray Ozzie and I did at the Brooklyn 6G Summit. I had a wonderful fireside chat with Ray Ozzie. Ray Ozzie was like a pioneer. He sold companies to Microsoft, a CTO of Microsoft. He's working on a company that makes this tiny chip, and he talks about it in his talk. a tiny chip that is very low data rate and will ride on the 5G IoT. He's doing it on 4G now, but his goal is, I'm sure, to get into 5G. So we'll have new things that we never had in 5G. And 6G, I believe it will be both a better PHY, much faster, another order of magnitude, getting close to the human brain by 2030, I believe, on the order of within a few orders of magnitude, human brain processing. I've talked about that. And then at the same time, it's going to be a new network architecture, because I think 5G is going to try to get stuff out to the edge, but then 6G is going to perfect that with computing, machine learning, edge content, edge delivery. That's my view. I wonder what Anna and Angel think about that.
Well,
Yeah, sorry. Go ahead,
I
Anna.
think part of this is already in 4G. I mean, you are a super fan of 5G and I am of 4G because the IoT is already in 4G. I mean, it is true that 5G has new features. I completely agree. But we can still get a lot from 4G that keeps evolving. So it's not that completely new. And at the end, it could have been an evolution of 4G. If we could, if we wanted. And you say, of course, 6G is going to be fantastic, but it could be an evolution of 5G, because at the end, as you say, we need to perfection all these new ideas that are new. IoT was already 4G, I would say. But anyway, I agree that we will see great things for sure.
No, I'm with that on this. So what happens is that so far 5G is being deployed and used as an extension of 4G. So we're still not seeing its full potential, I think. So it's still being used mostly to provide broadband access. So I suppose at some point we're going to see, network slicing and machine traffic and all the verticals mostly, right? I mean, factories, automotive, like cars. In Germany, they have auction spectrum for private use by factories, which is something also very new, I think. So, your BMW in Germany, you don't have to use Deutsche Telekom. You can run your own private network, all 5G. This is so there's disruptive aspects, I think, which are not so much technical. They have to do with what the standard aims to accomplish. But we're not seeing that yet. I mean, in Europe, we're not even seeing millimeter wave yet. I mean, we're just seeing sub 6 gigahertz. So right now, here in Spain, for instance, 5G is underperforming 4G.
That's why you both kind of are not happy with 5G.
Yet.
Not yet.
I mean, you guys, right? You guys have millimeter wave service, right? In New York, for instance, right? How does it work?
It's lightning fast when you're close, as long as a bus doesn't go by. But even if a bus goes by, it drops down to 4G. And, it's pretty amazing. I mean, it's really mind-blowing speeds. And engineers are trying to figure out how to deploy the coverage, but it works really well. And, someone asked on a chat about NTN, which are non-terrestrial.
Yeah, I'm reading it right now.
These are like UAVs flying, United Aerial Vehicles, Nokia, Ericsson. These companies are making, flyable base stations. We actually used the consumption factor theory to analyze that it's better to have a repeater than a full base station for power efficiency on the whole link. We just published it. That was an example of using consumption factor theory in a whole system rather than a device or a circuit. But the fact is, there are going to use NTNs more and more for like cell on wheels, but in the sky. But I don't think it'll ever be like have its own standard application. I think it's a niche, it's emergency. So it will be in the standard, but just kind of use, kind of like Anna said, IoTs in 4G LTE. It's in there because people make the existing standard work for IoT. There's not a special super evolved multi-year standard process to optimize IoT and 4G. There's a little bit of it.
There's a comment in the chat now about satellites, and for those of us who are old enough, it's interesting to see this revival of satellites.
Let's talk about that. We have to talk about that. And we have to bring real theory to these crazy business people, don't we?
So you guys are old enough to remember Iridium and Globalstar?
Yes, right? Iridium.
Can I tell you a secret? I'll tell you a secret. I was a consultant I was a consultant
For which?
when the
Iridium or
Iridium,
Global
when Iridium was conceived. I get a phone call from someone who wanted me to analyze the concept of Iridium. And I said, this is insane. I said, the law of physics, going to physics, will never support it. And of course, $6 billion, and 6 years later, it went into bankruptcy. So, I mean, these people that with all this money floating around in the market still think they can make satellites work, and they don't get it. The whole idea of cellular is recreating smaller cells that reuse the same frequency, not beaming from 100 kilometers away.
But it's coming
But
back big time.
Yeah, because now I think there is, of course, there is a reason, and it is coverage, right? So where you don't have anything else, it is for sure cheaper to fly a satellite or whatever you can. So I see, usually it comes, from the satellite industry. From time to time, they try to push and find their way into the standards. But this time, at least they have these in 3GPP, there are these study groups, and it may happen, because until now it never happened, right? It was completely out of the standard. Now, probably because of the drones and all other things that also fly, and all them are NTM, it's getting spot, in the standard. And maybe for not for our cities, but for all these not densely populated areas or places where there is not at all any service, they can maybe play a role if they manage to get things at a reduced cost, because until now they were too costly. But maybe now with the new technology that you can even do this software-defined radio in the satellite, I'm talking, of course, about LEO, not GEO, right? Maybe it will happen, and they will find
So my advisor at Stanford, Don Cox, who was anti-satellite, used to say, in places where there are no cells, it's because there are no customers. So by definition, there's no business, right?
Yes, I agree. But I think it is maybe time to talk not only about business, and talk about people. And I mean, I understand, of course, we need to sell. Not you and I, but the operators and the manufacturers need to sell. But we still have all those many people that don't have the luxury of enjoying internet, and maybe it is time to think about them. I don't know.
Yeah, the problem is who pays for it.
Yeah.
So SpaceX.
Communications want to use balloons.
Balloons, yeah, there's these, Google had these, what was it called? Oh God.
Loon, I think it was Loon
Yeah,
Communications.
Loon.
Yeah.
Yeah, it was shut down. It was just shut down. I mean, I've always wondered about balloons because, the wind you don't control. So, you have to be very opportunistic about it, right?
Yeah.
I mean, the wind goes where it goes. But these guys, SpaceX and OneWorld, they want to deploy 4,000, 5,000, 6,000 satellites. It's very ambitious. I don't know. Somebody must have made the numbers.
No, short the stock. Short the stock and make a lot of money. It will never work. Yes, granted, it's good for high latency, big delay, low data rates for people that don't have service. Granted, it will never, ever, ever be on a par of terrestrial satellite, simply because of the distance involved. LEOs are several hundred kilometers away. And given that distance, you just don't ever possibly get the kind of spectral efficiency that will allow an allocated piece of spectrum to be used for high grade communications. So the only hope for that idea, and by the way, I just sent out the link to you, Don. That should be a better link for the power efficiency factor paper. I don't know why it's not working at NYU. Maybe I've been talking about it and people are starting to download it, and IEEE got nervous. But the bottom line is, it will work. Satellites have a potential of working if the beam forming gets so good up in space that they can deploy a lightweight satellite that can make such narrow beams that the illuminated area on the Earth becomes smaller than a kilometer. Figure a rural farming community, houses are maybe a kilometer away. If you could spot cell parts of the earth where there are only 1 or 2 homes, now you have the ability to get the capacity of cellular. You have to go up to the terahertz frequencies.
What
to
kind of
be able to
antenna do you
launch.
need, right?
That's what you need. That's all. But we don't have that today, and these people don't seem to get that. That's the only way to get capacity reuse in
I
space.
mean, Ted, you need a huge antenna for that.
Yeah, or a physically small antenna at a very huge
Ah.
frequency. Think directional, right, Anna? Think directional.
Yeah, but
as
I
we go
mean,
higher in frequency, you can do that.
how about the atmospheric attenuation at these frequencies? I mean, that's the problem, right?
Yes, thank you. We've just written a bunch of papers on that this year, studying the attenuation. You're right, the troposphere. God made the Earth in such a great way that we have this magic band from sea level to 10 kilometers called the troposphere. And that troposphere protects all of us from galactic radiation. It protects us from most harmful rays, although you need to use your ultraviolet sunscreen because some of those can pierce that troposphere. But once you get above 10 kilometers, you're bombarded by galactic radiation and all this ionizing radiation. In fact, Google the 5 most scary things to NASA about trip to Mars. It's radiation, cancer due to ionizing radiation. It's one of the 5 biggest hazards. It's being bombarded by all this galactic radiation. That's why I try not to fly now. Having been a leukemia survivor, I try not to fly because I don't like getting above 10,000 feet because now I'm getting bombarded, and you are too, by ionizing radiation. And it's all fine in low doses, but you know, I have a compromised immune system. So I like to take the train from Raleigh to New York when I come up to NYU from.
Good, it's also more sustainable.
Yeah, exactly. But here's the thing, that troposphere is the key to allowing terrestrial wireless to proliferate up above 100 gigahertz and to use spectrum up to 900 gigahertz, which I believe will be the mobile top end. I think in the next 3Gs, you know, 6, 7, and 8G, we'll go up to eventually 900 gigahertz carrier frequency and channel bandwidths of 10 to 50 gigahertz. And that beautiful tropospheric protection allows satellites that are up there looking at the weather and the rain and spying on people. They look way up there at a couple 100 kilometers, and all the terrestrial energy won't radiate up because we got this natural screen created by the troposphere. So the troposphere helps buffer us. It's very high attenuation, but if we stay low on the Earth, we'll be able to keep terrestrial operating and not interfering with the radiation. But it goes to your point, Angel, that we really cannot get those beams up there in space, because if we use that high carrier frequency to get the spot beams you need for capacity in the air, you can't penetrate the troposphere.
What do you think? I think someone was asking in the chat about free space optics, for example, that are now popular in satellite. Can they work? Could it be a solution, or is it the same problem with attenuation and the like?
Yeah, I'd short that stock too. I'll tell you why. The sun is the biggest noise source, and all reflectors of the sun. I'll leave it at that.
But how about indoors?
Definitely could work, don't you think? What do you think, Katie?
Well, I worked in indoor optical wireless
I remember.
communication.
I remember.
Yeah, so I think it's a cool thing. I think of it as like an extra lane on the highway. It's not going to replace the highway. It's just supplemental. And it's getting back to the energy problem. It's a green technology because you're having lights do double duty. They're both illuminating the room and they're sending you information. But I want to get back to energy and saving energy with these lust for higher data rates. How do you mentioned we can do higher data rates with lower energy, but what are some practical ways to get around that?
I wonder if we need to rethink the modulation, because we are always looking at spectral efficiency, high, and 256 QAM, 1000, and and this is of course power consuming, and maybe we should use more bandwidth and get very simple modulations. But I'm not sure, because Ted will explain that with higher bandwidth you have higher noise, and then I'm not completely sure what is best, if to have higher bandwidth simple communication or lower bandwidth higher spectral efficiency. Not fully sure.
I mean, there's a
here's the
trade-off,
beauty.
right?
The beauty of the consumption factor theory is at least now we have a way to experiment, run math, do analytical models, do simulations. We finally have a common language. This is the beauty of math. It's a common language to solve problems. So now we have a theory, the consumption factor theory, read the paper. Now we have a theory to answer those questions, Anna. Now we can try. In fact, it's all in there. We contemplate this idea. So now we have a way of doing that analysis. I don't know what the answer is going to be yet, but I do know that small cells, as we showed in that paper, small cells open up the ability to start getting overall improved power efficiency compared to today's networks.
So there's a fundamental trade-off, right, between power efficiency and spectrum efficiency. If you increase one, you reduce the other. So historically, spectrum was expensive and power was not a problem. So, you know, we heavily biased our designs towards spectrum efficiency and didn't worry too much about bandwidth efficiency. Everything was linear modulations, right?
You know, you're right. What you were just saying, Angel gave me an idea. I mean, this is what's great about these get-togethers. You know, I wish the COVID era was over so we could be doing this in public over a glass of fine wine or a glass of fine math. You know, the thing that just hit me is, has anyone done the simple analytical, you know, this would be a great information theory problem, like Elza or someone, or some student doing information. Think about it. What is the overall power consumption of a wireless system, which is today's base station to mobiles, versus a total base station having the same power consumption, same capability as mobiles? That is, what if you had a total peer-to-peer network versus kind of the cellular network? How does that power consumption over the whole network and amongst individual users work? That's an interesting theoretical problem. Maybe it's been solved. I've never seen it. I didn't look for it very hard 10 years ago, but I wonder if that exists in the literature. That seems like a great canonical problem to start answering some of those questions, doesn't it?
Yeah, I mean, we're moving towards giving more and more importance to power efficiency and less to spectrum efficiency. And as we said before, we incorporate power consumption, all the elements in that paper, not just the radiated power. And then the trade-off between that and the spectrum efficiency, I mean, that should be a follow-up to your paper, right? How does that trade-off?
Absolutely. We kind of tease that a little bit. We look at it a little bit, but don't really do any, we don't do any toy problems. We just kind of say this could be done. But we do a toy problem on a relay versus not a relay, using the whole link, including the channel. And we do a toy problem on a little transmitter design, you know, with different components having efficiencies. But we never did that. I mean, that's such a beautiful application. We should do that. I just thought of that. If we do peer-to-peer everywhere versus base to mobile and get real power levels, you start to get a handle on what future networks should look like. Should we keep doing more densification even if we don't need it? Should we do big cells if we can get away with it? No one's ever answered that. We haven't done the analytics, but we could do it now.
It's great news for our students, right? That there's still things to do.
Lots stuff to do. The physical layer is not dead.
The physical layer is not dead.
No.
Not
I'm
for
going to
sure.
quote John Chaffee on that.
Yeah.
But however, I think we should maybe complicate even more the problem and add the upper layers, because I wonder if we are not wasting a lot of power in the upper layers without paying attention. And maybe the whole problem, which is difficult, you know.
No one knows how to analyze it. You're exactly right. Now we can analyze it. I love that, Anna. How much is too much overhead, you know, from Phi to Mac to application? I mean, it's amazing. I've never heard that asked before. Good for you.
Do you think we're still stuck in the 7 layers? I mean, God didn't come down on the 8th day and make the 7th layers. Do you think there's a tendency to?
You might be right. We might have done it all wrong. It might be like fossil fuels before they invented solar panels.
I don't know. There's been many attempts at cross-layer design over the years and not much to show for them. So, you know, there must be a reason why layers exist.
Angel, no, come on. Look, cross-layer design is the key to 4G. It's the way we've been able to get 15 or 20% more bandwidth for free, you know, with all these little subtle things between the Phi and the Mac, checking the packet sizes, readjusting the modulation, reformatting. That's gotten us like 20% capacity for free. Granted, it's not orders of magnitude, but it has made a big difference on the PHY to Mac. And then you have the whole idea of scheduling. Scheduling opened up so much more power efficiency and capacity, which we got in 4G, which we weren't doing in 3G. So the whole idea of scheduling and then just knowing what different packets and bits are doing to rejigger, to readjust the modulation from 1024 QAM down to 256 QAM when the channel instantly is getting bad. That's given us a lot of gains. So cross-layer has been really big with the main advance of scheduling.
Scheduling, yes, okay.
No, you're right. Maybe, well, cross-layer was very popular and then went out of fashion, as usually happens. But without that name, we could look at it, because you're right. And perhaps now it is the time to go a little bit upper. Now that we understand how to make efficiency in PHY and Mac, go a little bit up, and maybe we will find the same kind of efficiency or even higher. But it is difficult to find people that understand all these interfaces between, and not to mention the whole system of end-to-end, of course. But it is important to tackle this, I think.
It's a language problem, isn't it? Understanding the different languages. Okay, I'm going to give one more question before I open it up to our audience, our great audience, and that is machine learning.
Oh. So
Machine learning is a big deal now.
The discussion about machine learning in communications, it's almost philosophical at some point.
Yes.
It's always fun, right?
Yes.
I think, so maybe I can get started. So I think the first thing to say is that as engineers, we just cannot ignore something that works, right? So machine learning is here to stay, and it's powerful. There's no denying that. But sometimes it makes me wonder, right? I mean, what are we giving up? Because, I mean, what kind of insights are we missing on the inner workings of problems and on the structure of good solutions? So, I think that we should exercise some restraint. There are applications where it makes a lot of sense, but, I see too many people that are rediscovering all results with machine learning. I mean, there is this anecdote, right, of a paper rediscovering QPSK, for instance. So right now, there's so much hype and so many papers being published that it's hard to tell the really interesting stuff from everything else.
I see this machine learning as a tool that you can apply to your problems. And depending on the problem, it may be helpful or not. I think it is probably more helpful when you really cannot do the analysis because it gets too complicated. There are people, when there are humans in the loop, and uncertainty because of the behavior of the human, for sure, you can do this machine learning. So upper layers, for sure, traffic, things like that. In the lower layers, sure, it can help us and perhaps even to rediscover things. I wonder about, of course, the power consumption and other things that, the amount of signaling you need to exchange to do this learning, how it consumes. And I'm a little bit skeptical about the improvements in physical layer or lower layers, because we know already a lot. We can do our analytics and we can build systems that work. But for sure, there are problems where it can help.
Well, many of you know that at NYU, we have this annual meeting called the Brooklyn 6G Summit. This year, we call it the Brooklyn 6G Summit. It's been Brooklyn 5G Summit since 2014. And IEEE TV broadcasts it live to thousands of people, and it's all on the web. You can see amazing talks by business leaders, academic leaders, really amazing content, all for free on IEEE TV. And Tom Marzetta, our current director of NYU Wireless, our research center, and Elza Urquip, this year opened up another part of our NYU Wireless outreach, and it was just a total research day. And we invited maybe 20 or 30 academics from around the world and some of our industrial affiliates who work in research, company research. We had this amazing 3-hour meeting with people around the world. And that question came up. We spent probably a half hour addressing machine learning, artificial intelligence, and could it ever say recreate a better phi than what we come up with analysis and simulation. We had a debate that lasted about 3 weeks. 3 weeks of emails, you know, with Elsa and Tom kind of coordinating this, and Tom poking the bear, like, you know, challenging people. It was a fascinating discussion. And what I learned from that, I gained a new respect for machine learning, in that those who are using it and who have some, it goes back to the math question that we started with. If you have some fundamentals on a model, some physics, if you will, some fundamentals that can make a good first estimate in the model, and you can kind of build on what works and what's known in the past. There are real proponents of machine learning that think it will really invent and create new capabilities that we would not have come up with on our own. It's almost like a petri dish for trying things that, based on physics, it looks at more dimensions that we could physically do. So I think this whole ML/AI movement will have great dividends in the hands of people that really understand the fundamentals, that understand the fundamentals as the basis. So that gives me, and it comes back to understanding math, not for math's sake, but for learning the intuition and the fundamentals.
Excellent. Okay, I'm going to open it up to the audience. Do we have any questions from the audience?
Well, there's a bunch of them in the chat.
Yeah, are there any you'd like to particularly address? So we have about LaserCom.
Yeah, Ibrahim agrees with me that even the people that design neural networks don't really understand why they work, which is true. Which is true. I mean, they're still trying to figure out why deep networks are so effective. But they are. That's the thing, right?
Yeah, the more you know, the less you understand how it's possible that this all can work, because it's so complex, right? But but we make it work with all this complexity. So
no, it's kind of like a Volkswagen versus today's car. You could fix a Volkswagen, but today's cars, you need to take it to the dealer because of all the chips and things involved, and that's like neural nets.
That's a good one.
Yeah.
I mean, with a longer term perspective, I think it's inevitable that machine learning starts taking over bits and pieces of the physical layer even. And it'll be interesting to see which parts surrender faster and which ones resist, right? I mean, there are physical layer functions that perform very close to optimum today, and they're very efficient, like modulation and demodulation. So it's hard to imagine them being replaced by a neural network, but who knows?
Yeah.
So many of our graduate students don't take careers in wireless communications. They go to Wall Street if they want to stay in New York. And they're running all these high frequency trading algorithms and making hundreds of millions of dollars a month. And these are probably machine learning algorithms. I wish we could go to Wall Street and find out what they're doing, because they're making money with it somehow. Is it machine learning? Does it work until it doesn't? How does it rescue itself? I mean, I think there's a lot to be learned by these proprietary Wall Streeters and bring that into the communication networks.
Yeah, except we cannot afford paying them, you know? We cannot afford them.
Yeah.
All right. More questions from the audience.
There's a question about cooperative transmission.
Yeah.
Yeah, that's an interesting one. I don't know much about network coding, but you know, cooperative transmission makes me think about Cloud RAN, which I think is also may be important also down the road. Maybe not so much for millimeter wave transmissions, because those are noise limited, but for sub 6 gigahertz, you get to a point that the only way to keep improving is by cooperation, because everything else is exhausted, right? Codification, modulation, MIMO, it's all loaded up already. So
I think you hit it on the head. In the the lower frequency range, I think there's huge opportunity for that eventually. But we did work for cooperative multipoint up at 73 gigahertz on the NYU campus, published a paper to see what would happen if you could do multiple links at the same time. And it's very hard to make a case for that. Even COMP, if you want to look at cooperative multipoint, COMP as it was multi-user tried in 4G, it wasn't true multi-user as you think about it. It's hard to get huge efficiency gains. So I think as we go higher and higher in frequency and wider bandwidths, I think that's going to be harder to do. You're not going to get enough diversity, but I think the lower bandwidth, lower frequency channels, I agree, Angel, that there could be some real value there with network coding, multiple user capability. And that may be the way that 5G and future generations keep getting value and increased data rate throughputs in the lower spectral bands. The higher spectral bands, I think, will be just relying more on the directional nature. It's a little more sparse, although you will be able to take advantage of the closer base stations on some cases. So I think that's a good point you made.
I wanted to ask you something, Ted, about sub-terahertz frequencies. As I understand it, one of the big problems is to generate power, right? I mean, more than a few milliwatts is just hard these days.
Yes.
Just because you're halfway between optical frequencies and sort of, ORF. So are you optimistic that we're going to find ways of producing, tens and hundreds of milliwatts, even watts?
I am. Yeah, this is work being done by a number of companies and a number of universities around the U.S., a lot of West Coast schools like UC Santa Barbara, Jim Walter and Mark Rodwell. A lot of Mark Rodwell students go to Teledyne. Teledyne has 140 gigahertz RF amplifiers. They're getting, I think, 10, 20 milliwatts out. They keep making it better. They keep finding ways to combine common base structures to get more and more power by stacking the amplifiers. In fact, Jim Buckwalter gave a really good seminar. If you know Jim, he gave a talk about his grounded base structure where you use stacked bases. And then I called him later. I said, Jim, with you, it's all about the bass. No trouble. He loved it. So I think he's starting to use that in talks. But the fact is, there's DARPA's funding these programs all around the country. Japan is really investing hard in it, in sub-terahertz RF amplification. It's really the RF amplifier that's hard. There's a program called T-Music. We wrote about it in our 2019 paper, 6G Opportunities and Challenge, which kind of started the whole 6G idea. And we talked about all those fundamental issues, making the antennas small enough physically with the antenna elements, dissipating the heat, getting the RF. And we talk about the T-Music program and some of the capabilities up to 600 gigahertz FT, 200 gigahertz RF. So yes, we will solve it. Just like no one thought we could ever put millimeter wave in a handset. Now you have Samsung, Apple, Qualcomm, all shipping products around the world with millimeter wave. And they'll get better every year.
Ted's optimism, right? I mean, if anyone is ever depressed, give Ted a call.
Yeah. Oh, but it is true that, that we always find the way. I mean, if you see the history of telecommunications, it's amazing in such a short period what we have achieved. So I'm confident that for sure we will get the power and we will get whatever. I don't know exactly when, but it will happen. Getting back to the cooperative question, Ted, you mentioned the comp that didn't work, right? But I think comp didn't work because it was not the right moment. And now we have all these CRAN and all this softwareization and all these capabilities of really coordinating many access points. And this can work. And truly, I think we will see these big efficiencies of many cooperative access points once we can really make them cooperate. So I think COMP was too early for the concept was fine, but the implementation wasn't.
I think the channel sparsity, though, is going to make COMP harder as we go higher and higher in frequencies with wider bandwidths. So I think COMP's real value will be down at the sub-6 gigahertz.
That makes sense.
Yeah.
I think so too. There's an interesting comment in the chat about, machine learning and information theory. And it's mind-boggling how information theory missed the boat on machine learning. And they let computer scientists and signal processing people own it. And now I guess they're getting into it. But for the longest time, it's very surprising how it's just completely muted the topic. And they are the ones who can shine some light on why this works and how.
And develop some theory, develop some concrete rules, kind of like.
The computer scientists are not going to do that, right?
Yeah.
These are the people that have to do it. So go for it.
The questions as well, the questions I was mentioning about energy efficiency or overhead, or these kinds of things that of course are not dealt with by the computer scientists, they should be done. Truly.
I agree with the chat that the frustrating thing about machine learning is like, it's hard to figure out why the heck it works. What's the mechanism behind it? So there was a comment in the chat about it. Yes.
Yeah.
So I'm going to unmute Ibrahim and have him ask a question. I'm going to ask him to unmute.
Yes,
there you go.
I'm here. Hope you can hear me okay. Wonderful to be listening to all you guys. The energy, Ted, is amazing. I wish I could hear you talk every day. It's just very, very inspiring.
That's not what my colleagues say. Believe me, my colleagues.
Well, I'm coming from industry, not academia. So there you go. I was just curious in terms of, so there's been a push on the government side, obviously, always, trying to, see how they can manage to, outpace commercial. And, I'd be surprised if that happens. But at the end of the day is there's a real big push for lasercom, and kind of, that whole hype about millimeter wave is really kind of pushed by those replacement of, inter-satellite links and what have you. But, do you see that, pushing the architecture of, future generations where basically terrestrial and space becomes kind of, homogeneous, maybe perhaps. So that's one. Regarding machine learning, another separate question, unsupervised, supervised, do we really understand the theory itself? I've had my, really kind of, it's very intriguing and it's lovely too, but we don't understand it yet. And I've yet to see like a really good book on this topic, honestly. And regarding the cooperative transmission, I was referring to interference alignment. So like the work that Professor Jafar did, how do you, it's obviously it's a nice, it looks really great on mathematically, it's very elegant, but can we implement that? So it's a three-part question for everybody.
Yeah, to address that last one, I think we're saying that when you get to higher and higher frequencies, you use narrow and narrow beams, there's less interference. So it's not so interference limited. So I think there's a real opportunity sub-6 on that interference. I'll take the free space optics issue, and optics makes total sense in space-based. The original Star Wars missile defense system, so much of that's optical because you're out in space and it's the sun, where the sun is, so you can always avoid that and you can avoid the sun. For mobile, I'm below the troposphere for reasons we talked about. I'm less bullish, so I don't see it ever being totally homogeneous with optical going up to space. Space to space makes great sense optical. Inside a building makes great sense optical. I'll let the others comment on the machine learning and the other point.
Well, I can comment on the IA, maybe, and the interference alignment, which is a beautiful theory, really. But it's an example of an asymptotic result that just, once you back off from infinite SNR, you find that there are better things to do with your degrees of freedom than interference alignment, right? So it hasn't quite found any application, sadly. So it has remained a wonderful theoretical result. There's other examples I could give you of asymptotic results, right? I mean, one has to be careful with asymptotics. I mean, we love them because everything simplifies in the limit, right? And you can get beautiful expressions, but one has to be aware that eventually you have to be able to back off from the limit and the result has to be robust. And sometimes it happens, and like massive MIMO is a good example, right? You can get asymptotic results and then you back off from infinite antennas to 60 antennas. It still works beautifully, right? but other times it doesn't happen.
This
Anna.
reminds me of a question this morning with my students. I asked how many antennas would you recommend or would you need for a hybrid beamforming versus the digital beamforming? And they say infinite. And I'm like, well, yeah, infinite, but infinite you cannot have. Do you realize? Anyway, and there is the question about the machine learning, right? I truly think machine learning is a tool. And when you use it as a tool, you really don't need to understand all how it works because you have a problem, and if your problem is well understood and the parameters are the right parameters and the model is the right model, it gives you the result that you can use. And I really don't mind if I don't understand how exactly it got this result. Of course, there are people that work on making the tool, and those need to understand the tool. But those who use the tool, we can go
Very
with it.
pragmatic.
Very pragmatic. And as long as you can trust it, I agree with you, Anna. I think that's a great point. Any more questions? I don't see any. You guys have been so good. We don't have any more questions. You've answered all the
Alright, well,
questions of the world.
dinner time, maybe for some of us.
Yeah, you're up
That's
late.
right. Well,
You
wanna
both,
thank you.
but you eat late in Spain, both of you. You
Yeah,
probably
it's
used to.
actually, this is about the usual dinner time, right, Anna?
Yeah.
So it's
Yeah.
about right.
Well, I sent my family out for dinner because otherwise this would be very noisy. So,
You
but
know what?
they are about to come back.
I miss you all. I miss seeing you all and
I do
know,
too.
we do,
karaoke,
Ted.
going dancing. I miss that. I can't
Oh,
wait
come
till
to
that.
Madrid.
You know,
There is Globcom. There is a wonderful excuse.
you know, I was gonna come and then I decided I still don't feel safe yet. I mean, I
Yeah.
was gonna come and I decided not to. I want to
Yeah.
go. I know you both will be there, right? You'll both be at
Mm.
Well,
Globecon.
Anna is the boss, so I'm sure she's gonna be there.
Yeah,
And I'm going
yeah.
to Anna. I'm coming.
Yes, it's going to be very nice, Angel, really. I mean, I understand some people cannot come, and what can we do, right? But the social events are amazing. I promise.
And we're
Yeah.
talking about GlobeCom for those in the audience who don't know what you're talking
Yeah,
about, which will be
sorry.
fabulous. But again, I'm not going either because
Yeah.
I don't feel safe yet either, but I applaud those who do. So I want to thank you all so much. I enjoyed this conversation. I learned a lot. You guys were awesome, guys and gals. And I want to let those of you who are still here are in January, we're going to have another panel. We're going up the stack and we're going to have Vince Cerf and Jennifer Rexford and Amin Vadat from Google and Alberto Leon Garcia. So it should be a very cool panel. Perhaps not as cool as this one, because this one was pretty darn cool, but a good panel. So with that, I'm going to thank you all, and I will see you next time. Bye.
Thank you.
Everyone.
Bye.
Bye. Bye. Thank you.